Chapter 5 States of Matter in 5.1 Gas. Next, students also should be able to define Dalton's law. Dalton's law of partial pressure. In a mixture of unreacting gases, the total pressure is the sum of the partial pressure of the individual gases. By the formula, P total equal to the sum of the partial pressure of A plus partial pressure of B plus partial pressure of C, and so on. Example, we have three types of the gases in a container. So the total pressure is P total equal to the sum of the partial pressure of the nitrogen gas plus with the partial pressure of the helium plus with the partial pressure of argon. So this animation shows a mixture of the two gases, which is we have steam and air. So the P total equal to the P steam plus with the P air, which for the partial pressure of the steam is 8 bar, while partial pressure for the air is 2 bar. So the P total is 10 bar. Okay, next, let's see a video.
Hi, this is Dr. McCord. I'm going to talk to you today about Dalton's law of partial pressures. We're going to start out with the ideal gas law, which is PV equals nRT. We're also going to solve for P here and just get it written in terms of the number of moles, the temperature, and the volume. We're also going to hold the temperature and volume constant so that we can split out the RT over V term. We're going to call that a constant, and this really allows us to kind of think about pressure only in terms of the number of moles. What that means is pressure is directly proportional to the number of moles. So it's real easy to think about the calculations here. So if you double the moles, you double the pressure. You triple the moles, you triple the pressure. You get the idea. So we're going to first start with a container here. If you need to know what the container size is and the temperature, we'll go ahead and give you that. 244.7 liters at 25 degrees C. Now we're going to put 1 mole into this container and we get 0.1 atmospheres of pressure. We're going to then double this up to 2 moles and we're going to get 0.2 atmospheres of pressure. And as you can guess, if we go to 3 moles, we get 0.3 atmospheres of pressure. And this becomes really easy to just keep going, count 4 moles, 5 moles, go all the way to 6 moles, you'll get 0.6 atmospheres of pressure. You go to 7, you'll get 0.7. And we'll take this all the way up to 8 just to make a point. But we really want to shift our focus now into several containers combining to make a mixture. So let's imagine we have 3 containers like this and explore Dalton's law of partial pressures. So here's 3 containers. We're going to label them A, B, and C for the gases that we're going to put in them. We're going to put 10 moles of gas A. We're going to put in 6 moles of gas B and 4 moles of gas C. That's going to give us 1 atmosphere for A, 0.6 atmospheres for B, and 0.4 atmospheres for C. We're also going to quit counting in moles. We don't need moles to do Dalton's law, so we're going to just think about it in terms of pressures. And now we're going to combine these amounts and make a mixture. So we're going to take each of these 3 containers and now push all those moles together into 1 container. It's easy to do the math. we now have 20 total moles in the container, and turns out that the pressures add up in the same exact way, and we get 2.0 atmospheres of pressure in the container. So to summarize, we've got 20 moles total, we've got 2 atmospheres of pressure. Now you need to remember the idle gas law does not care what kind of gases you have. So 20 moles gives you 20 atmospheres. Now I'm splitting things back out on the right to show you the separate containers, and I'm also showing you the mixture. I'm going to put a dividing line here to show you that there's the 2 different ways we think. On the left is what the mixture holds. We just count number of moles. We don't care what they are. But on the right is more of the way a chemist sees things when he's looking at a mixture. We really see it as the 3 separate partial pressures that combine to give the total pressures. That's exactly what Dalton's law is all about. So the way I see this is partial pressure of A, the partial pressure of B, and the partial pressure of C all combine to give the overall total pressure in the mixture. If I take all those quantities and make a mathematical relationship out of them, I have the very definition of Dalton's law of partial pressures. We can also state this law in words. Dalton's law simply says that the total pressure of a mixture of gases is equal to the sum of the partial pressures. It's a very handy law, and it works for as many gases as you have in a mixture as you want. This has been Dr. Paul McCord talking to you about Dalton's law of partial pressures. Have a good day.
Next, partial pressure. Pressure that a gas will exert if it was present alone in the container. Let's say we have nitrogen gas in a container with the partial pressure of the nitrogen gas is 1 atm. And we have another container with the argon gas with the partial pressure of the argon gas is 2 atm. Combining these 2 gases in a one container, so the total pressure is the sum of the partial pressure nitrogen gas plus partial pressure of the argon gas, that is 3 atm. Consider a case in which 2 gases A and B are in a container of fixed volume. So the pressure exerted by gas A and gas B is calculated by using the ideal gas equation. The partial pressure of A equal to the mole of A times to the gas constant times to the temperature over volume. The same formula is used to calculate the partial pressure of B. Application of the Dalton's law in collecting gas over water, also known as water displacement method. When a gas is collected over water, a mixture of the particular gas and water vapor is collected. By using the Dalton's law, P total equal to the sum of the partial pressure gas plus with the partial pressure of the H2O. From this picture, let's say we have a substance combusted in a conical flask and the gas is released into the round bottom flask. So above water, there are mixture of the gas and water vapor, and the P total equal to the P gas plus with the P H2O. Example, when potassium chlorate is heated, it decomposes to potassium chloride and oxygen gas. By equation, 2 mole of the potassium chlorate in solid state decomposes into 2 mole of the potassium chloride in solid state and 3 mole of the oxygen gas. The oxygen gas produced is collected by water displacement method. according to the Dalton's law of partial pressure, P total equal to the P oxygen plus with the P H2O. So P oxygen equal to the P total minus P H2O. At standard condition 25 degrees C, vapor pressure of water is 23.8 torr.
So here we have a diagram of what I'm talking about. We have a reaction in here of zinc with hydrochloric acid, a single displacement generating hydrogen bubbles. Those hydrogen bubbles would just escape out into the air, but we want to collect them. So we've put them into this tube, which we want them to go somewhere, so we will put them into this jar. And so this jar began full of water, but as we bubbled the hydrogen gas into it, it will push the water level down and down and down, and so we'll have a container full of hydrogen gas, and that's what we mean by collecting the gas over water. So now eventually this reaction will stop. We'll stop making hydrogens. Now we're full of whatever hydrogens we have in there, and so we want to measure the pressure of that hydrogen. Well, one of the things we can do that's pretty simple is we can actually look at the atmospheric pressure in the room, because the atmospheric pressure in the room is pushing down on this water level out here, causing this water to be pushed up into the chamber, up into the tube that we're collecting it in. But the reason that water can't go up any further is our hydrogen gas is pushing down on the water. And so as long as this water level is staying stationary, then we can assume that the pressure of the atmosphere and the pressure of our sample is the same. So they're equal. But, so you might just say, well, whatever the pressure of this hydrogen gas that I bubbled in here is just atmospheric pressure, easy enough. But we have a problem. If you see the label here, this says hydrogen plus water vapor. It's not only hydrogen that's pushing down this water. So we can't say that the hydrogen pressure, that the gas that we made, the hydrogen, the stuff we care about, we can't say it's equal to atmospheric pressure, because there's other stuff in there. At the surface of this water vapor, water is evaporating. And so there are now water molecules up in this chamber which are also pushing down on the water level. And so it's actually pushing a little bit harder than what just the hydrogen would push. And so we need to account for this. So we want to figure out what the hydrogen pressure is, because that's our sample. We want to find out what it is. But we got this water also happening. But one thing we do know is that the mixture here will push down equal to atmospheric pressure. So this turns out to be a Dalton's law problem. So we can say that the pressure of our hydrogen, now generally speaking this would be whatever your sample is, the hydrogen here. With this example you made hydrogen, but whatever your sample is would go here, plus the pressure of the water vapor is equal to the atmospheric pressure. So we would read the atmospheric pressure off of a barometer, and we would find the water vapor off of a table. There are actually tables for water vapor at various temperatures. And so we would need to know the temperature to do this. And so let's just kind of make up some examples. Let's say that the pressure, what we're going to do is take the formula we just had and solve to get the hydrogen pressure by subtracting off the vapor pressure. And that tells us to get the hydrogen pressure, we would take the atmospheric pressure minus the vapor pressure.
That's all. Thank you.